This video is basically going to be about what I think about tensors. Basically, they're amazing, and I want to show some neat properties that they have that allows us to prove a few things that we kind of struggle to prove using normie methods. Okay, so this video is mostly going to be for me in the future to come back and look at how retarded I was to basically see how badly I understood tensors. But if you understand something from this video, I mean, that's a bonus. So I'll start off with the most useless introduction to tensors. So from linear algebra, everyone has learned what a linear map is. So basically, a linear map is, damn it. So linear, oh my god. So a linear map is defined as a function from a one vector space to another vector space. So like, and the linear map holds a few neat properties, which is basically t of alpha plus beta equals to t alpha plus t beta, where alpha and beta are in V and t alpha and t beta are in W, and also t of lambda, damn it, t of lambda alpha is equals to lambda t alpha. So what is lambda? Lambda is basically a number in a field. So basically vector spaces are defined over certain fields. I have no idea how to write the symbol for field, but whatever. So basically both V and W are over a certain field, and basically a linear map holds these properties. So what are a few examples of a linear map? So one linear map could be the differentiation function. So suppose oh my god, I can't write a D. So suppose I like call D a function, and D is defined as a function from the vector space of polynomials to another vector space of polynomials. And this is a linear map. What is a multilinear map? So a multilinear map is defined in a similar way. So basically you have a function that acts on this a Cartesian product of multiple vector spaces over the same field. It doesn't make sense for them to be over different fields, or else it wouldn't be a multilinear map. So dot 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 maybe until Vn, and this gets sent over to another vector space. So tensors are a special type of multilinear map. So basically, I've been calling everything T, my goodness. Okay, so this is a tensor. So tensor is a special type of linear map. So over here, star means dual space. So this is going to be a Cartesian product of a bunch of dual spaces of the same vector space together with Cartesian product of the same vector space. And this gets sent to R. So the type of tensor is basically comes down to how many dual vector spaces there are and how many vector spaces there are. So if the tensor acts on maybe a R number of dual vector spaces, Cartesian products, and S number of vector spaces, then the tensor is of type Rs. So how will one visualize this? So if you take a tensor and you act on the following list, okay, let's call this omega 1, omega 2, dot dot dot, omega r, v1, v2. Why am I labeling the indices on top? To differentiate the dual vector space and the normal vector space. So basically, these are all vectors that belong to these vector spaces. So each of them are from the individual vector spaces. One cool thing about tensors is that they can give us the del operator. So if you know a bit of E&M and vector calculus, you will know that the del operator in Cartesian coordinates is pretty simple. It's just d by dx I hat plus d by dy j hat plus d by dz of k hat. But the gradient operator in spherical coordinates looks a bit more weird, where you have coefficients like 1 over r and 1 over r sine theta popping up for no reason. In weirder coordinates, the coefficients get worse. So the method used to derive these coefficients in vector calculus at least is quite complicated, and it's a normie method to get such coefficients. The tensor can help us skip a lot of steps. All you need to know is the metric tensor. So here is a short introduction to metric tensor. So the metric tensor is G mu nu, and it helps us generalize the dot product. So a dot product of suppose a vector A and a vector B is just going to be G mu nu A mu A nu, where A mu and A nu are where A mu nu are coefficients of the basis vector, which is not normalized. I'm assuming the knowledge of Einstein's summation convention. So this is simply going to be some mu index and some mu index, but for convenience, we will just exclude the summation symbols. For example, in Minkowski space, the dot product, suppose Ct xyz dot itself, Ct xyz, is going to give us Ct squared minus x squared minus y squared minus z squared. So this is not the usual Pythagoras theorem we see. That's because the metric tensor in Minkowski space, which you can also represent as eta mu nu, is equal to 1, negative 1, negative 1, negative 1, 0, 0. So the zeros, the big zeros basically represent that every element is 0 other than the diagonal elements. So this is the dot product, and the contrarian vector components, these guys, are going to be scaled down by the magnitude of their basis, the basis vectors of the contrarian vectors. So the basis vectors of the contrarian vectors are going to be these guys. So this is the basis vector, and it's scaled down by the magnitude of the basis vectors. So for convenience sake, let's call this H1, and there are three others, H2 and H2 others, sorry, H2 and H3, which are basically dr over d theta and dr over d phi. So the components are going to be scaled down divided by h divided by h. So we know that the metric tensor is going to be scaled up by h squared from the Kronecker delta in order to give us a dot product that is valid. So we know that the metric tensor in spherical coordinates is going to look like this: 1 r squared sine squared theta, where r and r sine theta and 1, these three, h1, h2, h3, h1 squared, h2 squared, and h3 squared. So this is h1 squared this is h2 squared, and this is h3 squared, where h1, h2, h3 are the magnitudes of the basis vectors of the contravariant vector. So now we have the metric tensor of the spherical coordinates. I'll just write it again. So g mu nu equals to 1 r squared sine squared theta 0, 0. So now we can get the del operator. First, we have to realize that the operator, which is d over d x mu, where x mu is the coordinate r, theta, or phi, is actually a covariant vector because it transforms as a covariant vector. As you can see, d, suppose I put phi, I mean not phi, sorry, that's already a coordinate. So suppose I put f, so it's df over dx prime mu dx prime mu over dx mu. So it transforms as a covariant vector. Of course, this is using Einstein's summation convention. So since this operator transforms as a covariant vector, we know that the del operator is the normal operator with the normalized basis vectors. All we have to do is just to get the component, suppose I would say the mu component, all we have to do is take 1 over h mu of the component of the covariant vector dx mu. So now we can write down the del operator in spherical coordinates, which is going to be 1 over h1 d over dr r hat plus 1 over h2 d over dr, sorry, d over d theta hat plus 1 over h3 d over d phi hat. And from this, we can get d over dr r hat plus 1 over r, sorry, yeah, 1 over r d over d theta hat plus 1 over r sine theta d over d phi hat, and get that.